Hi all. In the previous video, we had learned about support vector machines and we saw the linear case where given a set of data points belonging to class plus 1 and minus 1, we are able to find a linear decision boundary which separates our class 1 from our class minus 1. And the way we do it is that we find a margin which passes through the points which are closest to the decision boundary, and we try to maximize this distance. So essentially we train our model parameters in such a way that this distance is maximized. And the way we normalize our values is that this Ri is essentially given by inverse of the norm of this theta vector. So now this works perfectly well when our data set is perfectly separable using a linear decision boundary, but this is usually a artificial situation. Usually in most real life situations such linear decision boundaries do not perfectly separate our data into the two classes. So nonlinearities could be much more adverse, and we are going to see those situations also in this video. But to begin with, let's take the simple case where we have some data points which are lying on the other side of the decision boundary. So these blue points should actually be on the other side, but they are now here, and now there are also some green points which are present over here. So now the problem with these points is that they do not satisfy the constraints of our SVM problem, because if you remember, then our constraint for SVM was that this H or this quantity must be positive for all the points in class 1 and it must be negative for all the points in class minus 1. But because of these points over here, this constraint is no longer valid, and hence we need to update our constraint conditions. So what we do is to introduce what are called slack variables. So essentially, if the two classes are not linearly separable but nonlinearities are small. Remember, this does not work when nonlinearities are large, and then you have to use what are called kernels, which we will see in this video. But if the nonlinearities are small, you could make a minor variation to the linear SVM formulation and make it work for your problem. So what you do is to introduce slack variables xi I. So essentially what we now do is that earlier we had the condition that yi into theta 0 plus theta transpose xi must be greater than equal to 1 for all I. This was our situation in the previous case. But now we modify that and do a minus xi I over here. So this is kind of a small relaxation that we allow to our standard linear SVM condition. And of course, we insist that our xi I is greater than equal to 0, and because we don't want to be too generous, we also say that the summation of all these relaxation parameters must be less than or equal to some constant. So this is also a kind of regularization because we are allowing for a relaxation but within a certain boundary. So xi I is not allowed to become very, very large. So now essentially our problem is similar to what we had earlier, where we had minimization with respect to theta and theta naught of half norm of theta square such that above conditions are met. So this is again a constrained optimization problem like we had earlier. So in the linear SVM case, we had this minimization. This half is just for the sake of some simplification in the calculations and does not really have any fundamental significance. So earlier, for the standard linear SVM, we had this minimization subject to this constraint without the xi, of course. But now we have this xi term over here, and we have this additional constraint that our xi I must be positive and the summation over all xi i's must be less than or equal to a certain constant. So now again we use the same method of Lagrange multipliers but with three additional terms. So earlier we had this, and now we have to add this as well as this. So we have a new Lagrange function in this case. So sometimes it is also called the Lagrange primal function, and that is now given as half norm of theta square plus c times summation xi I. So this is to keep the xi I summation in check, minus summation mu I over xi I. So this is to ensure that all individual xi i's are positive. And then our most important condition, which is minus summation alpha I into yi theta 0 plus theta transpose xi minus 1 minus xi I. So what do we do? Like always, we first minimize this. Now theta, theta prime and xi I, and then finally we maximize that over alpha i's. Now you may ask, what about this c and mu I? So c has to be chosen by the user, like when we did regularization for the ridge and the lasso case, there was a regularization parameter lambda. This c is also a kind of a regularization parameter which you have to choose. How to find mu I? That we will see shortly. There will be a simple formula that will give you the value for mu I once you have found out the other parameters alpha I. So essentially, if your C is very, very large, then your xi i's will be forced to be very, very small, which means that you do not want to allow a large relaxation. You are being very, very strict. And if you want to allow a large relaxation, then you have to make C to be small. So again, what value of C is the most appropriate, that you have to figure out by trial and error. So now how do we carry out this minimization? Same thing, you just take a derivative of LD with respect to theta 0, theta and the xi i's, and then you will get some expression. You then substitute it back over here and you will then get the Lagrange dual objective function. So let us take the derivatives with respect to theta 0, theta and xi I of this Lagrange primal function. So when we do that, what we get is the following. So you have dou LD by dou theta 0 is equal to 0. And what does that imply? Like earlier, it is summation of alpha I times yi is equal to 0. Why is that so? Because theta 0 is only present over here. All these terms will go to 0 when you derivative with respect. All these terms will go to 0 when you take a derivative with respect to theta 0, and what will only remain is alpha I times yi. Now let's take a derivative with respect to theta vector. So this will go away, this will go away, this will go away. Again, like last time, what will just remain is this and this. So these two expressions are exactly the same as what we obtained in the linear SVM case without the slack variables. So what we get is that your theta is equal to summation of over I alpha I yi and xi. So now once again, so this xi is a vector and theta is also a vector of the same dimension. And like earlier, we choose alpha i's to be non-zero only for the support vectors. So this alpha I is 0 only for the xi's which lie on the margin. And then finally we take a derivative with respect to the xi i's. So dou LD by xi I is equal to 0, and what that will give you is that alpha I is equal to C minus mu I. Again, I'm not doing all these derivatives in detail. I am sure you can do it on your own. But just to get understanding that when you take a derivative with respect to xi I, this thing goes to 0, this thing goes to 0. What remains is your C from here, mu I from here, and alpha I from here. And that is what you see in the expression over here. And now let us substitute these expressions back into our expression for LD. And lo and behold, we get the exact same Lagrange dual objective function as what we saw in the previous video when we did not take into account any slack variables. So this LD is exactly the same. It is summation over I alpha I minus half summation over I summation over I prime alpha I prime yi prime xi transpose xi prime. So this is the Lagrange dual objective function. And this, as we mentioned, is concave. And our objective is to maximize this LD with respect to alpha I. And since it is a concave function and it has a unique maxima, this can be solved by using the methods of quadratic programming, also because this has quadratic terms in alpha I. So we are again not going to get into those methods, but just for your information, there are standard programming methods available to maximize this Lagrange dual objective function. So now there are just one more set of conditions which are required to do this job. As I mentioned that we choose our alpha i's to be non-zero only for the support vectors. And where does that come from? That comes from what is called the Karush-Kuhn-Tucker conditions. So again, we are not going to derive these conditions, but I am going to only state these conditions, and it can be shown that these conditions are essential to ensure that the values that we get finally are the ones which lead to an optimum solution. So what are these conditions? These conditions are alpha I times yi theta 0 plus theta transpose xi minus 1 minus xi I, this is equal to 0, mu I xi I is equal to 0, and our yi times theta 0 plus theta transpose xi minus 1 minus xi I, this is greater than equal to 0. So all of this is for all I. So this last one, of course, we have already seen earlier. This we used for our definition of the Lagrange function also. But these two are additional conditions which are provided, which help us in reaching the most optimum value of our parameters. Now you can see that for points which are off the decision boundary, for them this quantity will be non-zero, and so in order to satisfy this condition, alpha I has to be 0 for all those points which are off the margin. But for points which are on the margin, for them these values are 0, and for them our alpha I can be non-zero. So this is how we ensure that we only take care of the support vectors to find our model parameters, and that is why this method is called as the support vector machine. So now the question comes, okay, that we have been able to handle a small amount of nonlinearity using this method, but what happens when the nonlinearity becomes very, very large? And the answer to that is in this very simple expression, which is xi transpose into xi prime. Now, if you remember, the primary way or the simple way by which nonlinearities can be handled in logistic regression also is by doing a transformation of variables. You could use that for linear regression also, that you transform your variables to a new set of feature vectors, and then in that space one can expect that the problem will be linearly separable. But that may not always be the case. You may not know a priori what the variable transformation would be. In SVM, the good news is that you do not need to know the transformation function, because all that this Lagrange objective function depends on is this inner product of xi with xi prime. So if you could define this inner product differently, you would get a different decision boundary which can be nonlinear for certain choices of your inner product function, because this is the usual definition of inner product, but you could define inner product in any whichever way that you like. So essentially what we do is that we replace our inner product in the Lagrange dual objective function by the kernel function. So what we write is that our LD, which is the dual objective function, is equal to summation over I alpha I minus summation over I, there's a half also, summation over I prime alpha I prime yi prime times a kernel function of xi and xi prime. And now you have converted this into a nonlinear decision boundary problem. Now in this case, how do you estimate your hypothesis hi, which is h of theta and xi, and given as theta naught plus theta transpose xi. So now what we had found just now is that your theta is given by summation over I prime, alpha I prime, yi prime and xi prime. We are using I prime over here just to differentiate that from this I, because this index I and this index I prime have to be different. So now this is equal to theta 0 plus summation over I prime alpha I prime yi prime xi prime transpose times xi, and now we replace that by the same kernel function. So this becomes theta 0 plus summation over I prime alpha I prime yi prime times the kernel function xi prime times xi. But since the kernel function is symmetric, so this is equal to this. So once you define the kernel function, you can now estimate your hi and ld without knowing the actual transformation. And for many of the kernels that you use in practice in SVM, the transformation function is actually not defined. So let's see what are some of the important kernel functions that one can use. So there are kernel functions. For example, one could use a polynomial kernel function. So you could have a dth degree polynomial, in which case your kernel k of xi comma xi prime is given as 1 plus the usual inner product of xi comma xi prime to the power d. You could also have what is called the sigmoid kernel, which is given by your k xi comma xi prime is equal to tan hyperbolic of some parameter gamma 1 into xi comma xi prime inner product plus some another variable gamma 2. So these are some kernel functions that are useful in some problems, but the most commonly used kernel functions is what is called the radial basis function. In short, it is denoted by RBF, and it is also called the Gaussian kernel. No matter where you go, the Gaussian follows you. So this radial basis function xi comma xi prime is given as exponential of minus some parameter gamma into xi minus xi mod square. So this is the Euclidean distance between xi and xi prime, and the square of that multiplied by a factor gamma. So this gamma is sometimes called the kernel bandwidth. So although, as I said, there are other kernel functions also available apart from the two others which I showed, but in SVM problems the RBF is the first default choice, and you worry about other kernel functions only if this one does not work. So this is the most widely used kernel function because this has in some sense an infinite amount of flexibility. So if you choose your gamma to be very, very high, then this leads to an arbitrarily complex nonlinear decision boundary, because then every small distance between the points xi and xi prime is penalized very, very heavily, because if gamma is high, then even if this is a very, very small number, your exponential will go to 0, obviously assuming that your gamma is always positive. And one more reason why this is popular is because this is based on the Euclidean distance, and so has some nice properties which are useful in many SVM classification problems. So the graph that you see on your screen is an example of a SVM classification problem. And here, as you can see, as you increase the value for gamma, your decision boundary becomes more and more complex. And if your gamma becomes very, very large, essentially your problem becomes perfectly separable. So essentially, as your gamma becomes larger, your RBF kernel in SVM is even able to correctly classify problems which are highly, highly nonlinear, meaning amongst a collection of points which are in category -1. If you had even one point which was in category +1, this would also correctly classify that. So in some sense, as your gamma becomes very, very large, that leads to the problem of overfitting, because you are trying to become very, very tightly glued to the particular data that you have. And it may become difficult to generalize to a new data point. So now in SVM, choosing an appropriate value of gamma becomes very, very crucial for this reason, so that you can avoid the problem of overfitting. So this was a brief introduction to the case of support vector machines. But again, in order to really understand what's going on, you have to write the code. So a Python code example is there in the description box. Please take a look, write the code on your own, so that you can deepen your understanding of this very beautiful subject. So in the next videos, we are going to learn some other methods of machine learning. So till then, stay connected.